Why are they 7 and 1? Don't follow it closely enough to know why.
I think a big part of it is that Justin Jefferson, one of the wide receivers, he's a rookie. Well, no, he's been, I think it's his third year now, and he's like just, he had like the best rookie year wide receiver ever or something like that. He's just been
All
really
right.
good. So he draws like, most of the time he's drawing like 2 defenders on him. So
Okay.
he makes a lot of space and still makes catches. So
Cool.
that's a big part of it.
So today we're just going to cover the 0-1 knapsack problem, a dynamic programming solution to it. And just to recall our memories here, I forget whether or not it was part of your assignment on, like your first assignment or not, to do the 0-1 knapsack, a brute force method for it. I think it was, but in any case, let's remind ourselves what it looks like. That you are given a sequence of items here, or a set of items. Each one of them has a weight, and each one of them has a value. And overall, you're given a weight capacity. And if you consider all possible subsets, those are all possible solutions to the 0-1 knapsack, but not all of them are going to be feasible. For example, if you take, say, A1, A2, and A3, right? Then that total weight is going to be 5 plus 2 plus 4. That's going to be way too much, right? That's going to be 11. And so it's infeasible because it violates your weight capacity already, right? You can go ahead and say take A1 and A2, and that weight there will be 7, which is feasible, but is that the best that you can do? Right? Well, here's another one. What if we didn't take A1, the most valuable thing? What if we instead took A2, A4, and A5? That weight is going to be 2, 2, and 3. So it meets it perfectly, and so it's feasible. But the value is, or what's the value here? Sorry. What was the value for, that's going to be 15? And so the value here is going to be 5 plus 7 plus 7. Is it? Oh, is it? 19. You're right. Right. So this is optimal. Right. So that's the situation, that you want to take as much as you can, subject to that weight capacity, but you also want to optimize the total number of, or the total sum of all the value of things that you're taking. Okay. So now what we're going to do is we're going to develop a dynamic programming solution. Dynamic programming solution. We start out with that FAST method. First, I forget what it stands for, but the F is for the first solution. So what I'm going to do is I'm going to establish a recurrence, V sub I, J. This is going to be the value of the optimal solution involving items A1, A2, dot, 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 up to and including AI. So it might be some subset of that. You're not going to be able to take everything. Just like we saw here, I wasn't able to take the first 3 elements, right? So once I took the first 2, that was it. I'm done, right? I've reheated my weight capacity, and I'm not going to be able to take A3, A4, A5, right? So it's going to be involving some subset of A1 through AI with intermediate weight capacity of J. In other words, I'm going to artificially limit your weight. Right now, the weight capacity is, say, 7. I'm going to limit that even further. What if your weight was only 1? What if your weight was only 2? What if your weight capacity was 3, 4, 5, all the way up to the full weight capacity? So the bounds here, let's identify those next, are going to be, I is going to be 1 up to n, right? For each item A sub I. Right? Your bounds on j are going to run from 0 up to w, right? So 0 weight capacity, 1 capacity, dot, 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 up to the actual weight capacity w, which is part of the input, okay? You can't go beyond w because then that would be, right, violating that capacity right there. We start at 0 because we need to start somewhere. We need to start, in fact, we're going to start, let me go ahead and put 0 here as well, right? For each item ace of 1, for 0, that's going to correspond to the empty set. Right? If you're not considering any item, then that means that you're looking at what's the value of taking nothing, right? What's the value of being honest? 0, right? You're not stealing anything, okay? Okay, so based on those bounds, that kind of tells us what kind of tableau or table that we've got. Before we do that, though, let's consider the edge cases. Oops. The edge cases or base cases. Remember, we're looking at this recursively. The v sub ij is going to be defined in terms of previous solutions, okay? So we need to define some of those, the edge cases, though, in order to fill out a table, okay? So what if I give you, say, v sub I and j minus 1? I minus 1, I think? No, here, let me redo this. Oops. V sub I, or no, sorry, the other extreme elements. V sub 0 and j, and v sub I and 0. Okay? So what is the value, what is the value of considering no items, or no items, right? In other words, you're starting out at I as 0. The items are 1, 2, dot, 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 an. So what if you don't consider any of them? What's the value? 0. All right? Because you didn't take anything. Again, what's the value of being honest? What if you don't have any weight capacity at all? You can't carry even a single item. What is the value? 0, right? This is no capacity. Right? This suggests a table. Yeah, go ahead.
J is dependent on I, so if I is 0, then J
Well, for any, it doesn't matter what weight. If you had a weight capacity of 5, but you didn't take anything.
okay.
If you had a weight capacity of 10, but you didn't take anything, right? So they're independent. This suggests a table that looks something like this. I'm just going to go ahead and grab it. All right, there we go. Ignore the inner workings of this table here for a second. There are our corner cases, right? When I is 0, then you're not taking anything, and that's all those values are going to be 0. When j is 0, or when j is 0, then you can't carry anything, and these all end up being 0. Otherwise, they run from 1 up to n on I, right? Because you are taking items a1, a2, dot, dot, dot. This is item ai minus 1, ai, and then item an. These are weight capacities, right? So these are capacities. And they run up to w over here, okay? Now it falls to us to come up with that recurrence. So consider v sub ij in general. What is it going to equal? Well, remember that v sub ij is the value, the optimal value of the 0, 1 knapsack, considering items A1 through AI with capacity J. Right? You can carry J elements, okay? So now what we've got to do is we've got a choices. Right? Should we include item AI, or should we exclude item AI. Okay? Well, let's focus on this first one here. Should we include it? The first question that we should ask ourselves, sub-question here, is, can we? Can we include a sub I? So, how would I go about answering that question? Yep, so the weight of a sub I, if when added, is it feasible? All right? So suppose that we did. All right? So what is the weight capacity is J. All right? This is the intermediate weight capacity. What's the weight of the ith element? We'll just call that Wi. That's the weight of ith element. So if I were to take it, then what is the remaining weight capacity? It's the difference between those two things. Right? So this is equal to the remaining weight capacity. Now tell me, what does that have to be in order for this to be feasible, for us to take this item? So if I've got a weight capacity of 5, and I decide to include, or try to include, an item that is of weight 10, can I do it? Nope, because 5, my weight capacity, minus 10 would be negative. Right? So if J minus Wi is greater than or equal to 0, then it is feasible to do so. Otherwise, else, if J minus Wi is less than 0, it is not feasible. Right? So if it's not feasible, then automatically what's our choice? Do we have a choice? Nope. So we have to exclude the item a sub I. Right? Okay, let's suppose that we exclude a sub I. Then what is the value of v sub ij in terms of previous values? So we excluded it. Does that change our weight? It would not change the weight, right? But we've already considered items A1 through AI minus 1, and now we're considering AI. So what's the optimal value so far when we exclude this item right here? I minus 1, right? So again, we're considering A1, A2, A3, up to A sub I minus 1. And now we're considering A sub I. There is some value here, right? That value is equal to v sub I minus 1 because I'm only considering up to I minus 1. And since I'm not taking A sub I still have a weight capacity of J. Okay? So if I exclude, right? If I exclude A sub I, right, then that gives me this value right here. Right? If it's infeasible, or if I choose not to take it. Okay? What about if we included it? Include A sub I. Once again, remember that we've considered A1, A2, A sub I minus 1, and now we're considering A sub I. And we've chosen to include it. Okay? What is my value now? Well, what's the value of A sub I? Because I need to add that to my total. V sub I, right? That's the value of A sub I. And I've included it. Plus, what? Yeah, whatever previous was there. Now, what was previous? To understand that, let's look at the weight. By choosing to include A sub I, I've reduced my weight capacity. j minus w sub I. This is the weight remaining, let me call it remaining weight capacity after taking a sub I. Now that's not immediately backwards, right? That's somewhere over here, right? Because there's some weight capacity and I jump all the way back somewhere else. Well, with respect to weights, right? So altogether here, v sub ij, if I included I, is going to be the value of I minus 1 j minus w sub I. Okay, if we choose to include it. Okay, let's bring all of these things together. Because you chose to include this, so what is it with the rest of them? Right? Let's reinterpret this. This is the value of items A1, A2, dot, 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 AI minus 1 with capacity J minus WI. So I don't want to exclude any other item, right? Well, okay. Right? Yeah, go ahead. This one right here, that's the weight. So we've got, the setup here is that we've got items, weights, and values. These items are, that's a set. This is a weight vector, and these are value vector. Right? So for example, A2 has weight 2, which is equal to 2, and value V2, which is equal to 5, right? That one right there. Okay? And then here's our table again. There's the items, right? There's this index running from 0 up to n, and here are the weight capacities. You start out assuming that you can't carry anything. Now you can carry 1 pound. Now you can carry 2 pounds, 3 pounds, 4 pounds, dot, dot, dot. Now what if you can carry W pounds, right? And these are all the potential values, optimal values here. Now back to this one, where was it? Yeah, here we go. That choosing to take A sub I means that we only have to consider these items here. But our weight capacity has changed because we've chosen to take A sub I by reducing from J to taking off whatever weight the ith element is. All right?
So we're subtracting the weight
Right.
from J, but we're not adding value I, are we?
Not yet. Right? So let's bring those together. Right? So I have a decision to make, right? If it's feasible, right? If J minus WI is greater than or is equal to 0, then I have a choice. I can take A sub I, or I can leave it. Right? So that's going to be a max among the value of A sub I minus 1, J minus WI, right? And V sub I minus 1, J. Right? So let's annotate this. This one over here, you take A sub I. This one right here, you exclude A sub I. Right? Basically, if the value is greater if you leave that item because that's a low valued item or something like that, you're retaining the same weight capacity here, and then you're looking because you're saying, all right, well, I don't know if I should take it or not, so I'm going to go ahead and record whatever the previous maximum value was, and then later on, if there's a better choice, then I'll go ahead and use that weight capacity for a better item. Right? If it's not feasible, j minus wi is less than 0, then I have no choice. It's going to be v sub I minus 1 j. Right? Among all those. All right, and then this one is, again, this is excluding AI because you don't have a choice. Here we have it's feasible to take a sub I, which is better. Sorry, I think you're right. If you take it, then what do? You add in the value. Is that what you meant? Yeah, okay, sorry. That was coming to the end here, right? We'll add the value, right? We'll add the value to whatever previous value there was. Sorry, and then I completely omitted it over here. There we go. Let me rewrite this as gold. You take it, a sub I, right? And so you add in its value, and let's annotate all of that there, right? That's going to be the value, or the optimal value, of items A1, A2, dot, 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 AI minus 1 with capacity J minus WI plus the value of A sub I, which is equal to V sub I. Okay. Is that better?
Yeah.
Okay.
What's the difference between like, the second case and the third case?
There's no difference in the value. It's just your choice, right? I could take it, but I'm not going to because this ends up being greater than this. Right? I found a solution with a higher value than if I had taken this item. This item is worth like $1, but I already found a solution previous to this that was worth $5. Right? This is worth $1, but by reducing my weight capacity, I'm only able to pull items that are worth $2 or something like that. Right? So for example, and I'll annotate it with another color here, green. Suppose that this was of value 2, and then this is worth $1, but this one over here was worth $5. Right? Which one do you want? The one that has greater value. Ignore that item because it's so low valued and it's so high weight that I'm only able to take something else worth $2.
So you're comparing versus V sub I minus 1 in both cases. How could one be 2 and 5?
Well, because the weight capacity is different, right? So, for example, if I've got V sub 3, 2, V sub 3, 8, right? This is considering items 1, 2, and 3, 1, 2, and 3, but I can only carry 2 pounds. Here I can carry 8 pounds.
So even though they're both V sub 3, one might be only carrying A1, one might carry 9.
Yeah, it's some subset, right?
Okay.
This is some subset of items A1 here, over here, right? A1 through A1 through AI minus 1. You're not taking them all necessarily because you can't, right? You're just taking some subset. I don't know what that subset is. We'll have to rebuild that subset based on this solution. Right? There, okay. So our current solution here depends on this solution and this solution. Where are those with respect to the table? So let's bring that table back in here. There we go. There it is. So my solution right here is V sub ij. Okay. V sub I minus 1, that's just going to be one row up. Right? V sub j is going to be in the exact same column here. And then j minus I, wi, is going to be in the same row somewhere over here, right? I don't know where. It all really depends on w sub I. It could be 1 column over. It could be 5 columns over. It could be all the way back at the beginning. If it's infeasible, where is it? It's outside this table. Right? That's why we don't consider it. So this, this value depends on this one and this one. You're taking the max between these two. Yeah, go ahead. Here's the recurrence, right? V sub ij. And it depends on this one and this one. Right? And so with respect to this table here where I've got items A naught, so in other words, empty set, A1, A2, dot, 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 AI minus 1, AI, AN, right? Then all you're doing is saying, well, okay, I'm considering A sub I now. Right? I want to consider all subsets previous to that consist of elements 1 through I minus 1. Well, that's just one row up, right? And one row up. But now the weight, suppose that you don't take it, right? So this one is you don't include A sub I. This one over here is you do. Let me switch back to gold there. You do take A sub I. Right? So you're considering all subsets consisting of A1 through AI minus 1. But now by choosing to take A sub I, you have reduced your weight capacity. Right? So you go backwards in weight capacity over here to J minus WI. That visualization is nothing more than showing us what order do we need to fill this table out in. Remember, these are the base cases. The first column and the first row are the base cases. So if each element depends on elements in the row before it, what do we do? Top to bottom, left to right. Right. So let's write the pseudocode to do that. I and J. Should be pretty easy. For I running from 0 up to n, that's on the column wise for each row. For j running from 0 up to w, right, do the following. All right, you're going to v sub ij here is going to end up being the maximum among these. So you need to first check for feasibility. If j minus w sub I is greater than or equal to 0, then you have a choice, right? Taking A sub I is feasible, right? Otherwise, else, if j minus w sub I is less than 0, you don't have to do that as a check, but I'm putting it in here just to be explicit about it. Then v sub ij ends up being v sub I minus 1 j. Right? Again, if it's not feasible, then you have no choice. Don't take A sub I, in which case the value is just copied from the one right above it. Okay? Otherwise, you do have a choice. So you need to take the maximum. Right? Let's see. V sub I j will end up being the maximum among v sub I minus 1, j minus w sub I, and v sub I minus 1, j. Of those two things. Right? Here you take it. Here you leave it. Okay? All right. Questions on that so far? Otherwise, that's it. That's the pseudocode, right? Be careful, though, because if I is 0 or if j is 0, then it's a base case. V sub ij is 0, right? So this is the base case. You want to make sure that, if you're here, you're not jumping over here at all, right? Or if you're up here, you're not jumping up over beyond that table. So if you want to, you can iterate through and set all these values, and be done with it. or you can go ahead and integrate that into your for loops here. And if you did it outside of these two for loops, then you would change these to 1 and 1. Okay. Before we talk about how we can, an example or how we can regenerate this solution, let's do an analysis. Well, you're just filling out this table, right? So tell me, how long does it take to fill out this table? How big is this table, first of all? Table size is n times w, n plus 1, w plus 1. Ignore those, right? So, therefore, it is order nw. So, is it order n? In other words, it's linear? No.
Depends on what W is.
Yeah, oh, good.
There's not really a relation between n and w, is there?
Yeah, there's not really a relation between n and w, is there? We could put a bound on it, though, right? So, there are n elements
So
in the input. How? Oh, okay. Well, it's just strictly going to be w. But how big could w be with respect to n?
The maximum object weight times n.
The sum of all the weights of the items for w, if w is smaller than that sum.
Right. Okay. So we could so let's take w because that's actually part of the input, right? So since I've got n elements in the input, right? The input size is n, right? So the input size, we'll just call that n and simplify it. But now if I give you n bits, with n bits, what is the max value of the w, or max value that w that could be represented, that could be represented with w? Okay, that's how many bits it takes to represent a number. Think in reverse of that. What if I gave you, say, 1, 2, what if I gave you 5 bits? The max value that you could represent is that, which is what? 2 to the 5 minus 1, right? Right? If I gave you n bits, it's going to be 2 to the n minus 1. Let's ignore that because of big O. Right? So this is actually order n 2 to the n. Right? Why? Because both of those are part of the input, and w is not bounded. W is only bounded by n, but n, you could use that many bits to represent w.
Well, they're two different n's. One is the
Right, but I'm saying, what if, all right, so n is part of the input, right? You can't get by that. Now, granted, there are numbers associated with n, right? So log n, let's say. Right? Those are kind of irrelevant, though. The number of elements is what's important. The weight here, right? It could be as big as 2 to the n, because if I gave you, here's half the input, all right? The elements, n elements. Now, what if the other half of the input was a representation of w, because that's part of the input? And I'm saying, well, okay, well, if it's half and half, then I could give you n bits, right? And if I gave you n bits, then you could represent a huge number here. In which case, that table becomes exponentially large, right? It's not a square table, right? There are n elements here, but there might be 2 to the n elements over here. For that reason, this is called pseudo polynomial. Pseudo. Okay, spell it. Pseudo. Pseudo linear, right? It's a fake linear, right? Because order nw. Oh, w must be a constant. It doesn't have to be a constant, right? It's not bounded, and it could be up to 2 to the n. And so actually it could be exponential. Could be exponential. But if you consider W to be a not part of the input, right? And you're not bound by it, okay, well then it's linear. It's just that it's going to take you a hell of a long time to fill out this huge, long table, right? You're not exactly considering every single possible subset. It's not 2 to the, I mean, you're not generating every possible subset of 2 to the n. What you're doing is you're considering every possible weight capacity 2 to the n, right? And so that's why we call it fake linear, pseudo-linear. It could end up being exponential here. And in fact, the 0-1 knapsack problem is NP complete. Or NP hard, whatever you want to call it, right? In other words, order n, that's not right. Right? It's not part of a parameterized complexity. Right? Yeah.
Is that because you can put any weight you want?
Exactly. I could say, well, here are only 5 items, but I'll give you a weight capacity of 100, right? And then you have to do 5 times 100, and it's way longer than it is deep, shallow, whatever. So the last piece of the puzzle here is, well, we do need to build the solution, right? So here's our original input, and if you simulate this algorithm on that input, you will get a table that looks like this. I'll put it right here. There we go. Now, with our optimal binary search tree, we kept track of this root table over here that told us which element gave you that optimal value, and that one's your root. Here, we didn't keep track of another root table, did we? Right? That's okay, because what we can do is we can rebuild the solution. The last solution down here is a value 19, okay? What items, A1, A2, A3, A4, A5, are part of that solution? Well, do you remember? I think it gave it to you already, right? Way back here. What was the actual solution? Where is it? All right, we've gone way too far. Come on. There it is. There's 19. It's going to be 2, 4, and 5. Okay? Now, how do we actually compute that given this final table right here? Well, we start at the lower right corner, right? And then we look immediately above it. Those two values are not the same. What does that imply? That implies that we took this element, right? Because there's a change here. If there were no change, what would that mean? We would have simply copied this down, right? Because either it's not feasible or we chose not to take it. For example, right here, going from 2 to 3, right? That means that taking 3 was not feasible after taking 1 and 2. Why? If you take 1 and 2, what is your weight capacity? 7. And remember that the original weight capacity here was 7, right? Right there. And so once you've filled your knapsack with taking 1 and 2, right? Then you can't take the third item here anymore. Okay? All right, so that means that we took A5. Here's my solution over here. I'm building it as I go. Okay? So I come up here and say, okay, well, I took A5. What's my new weight capacity? Originally, the full weight capacity is 7 here, but by taking a sub 5, then my weight capacity has been reduced by 3. So I come over here, 1, 2, 3, to weight capacity 4 now. And then I look above again. Is there a change? Yep. So what does that mean? That I took A4. Right. Now, by taking A4, how has my weight capacity changed? 2. So I go over 1, 2. Right. Now, again, I repeat. I look up. Did I take A2? Or sorry, did I take A3? Nope, because there's no change here. All right, so we go up. Now I'm right here. And I look above that. Did I take A2? Yes, because there's a difference between 0 and 5. So I add A2 to my solution. By taking A2, my weight capacity now has changed from 2 to where? 0. At that point, I'm done. If you ever fall into this first column, that means that you have no more items to consider. If you ever fall into this, that means that you have no more weight capacity to work with. If you ever fall into the first row, that means that you've considered everything already. So if you ever fall into either one of those or go out of the bounds of this table, then you're done. And there's my full solution right there. Yeah.
Can we just go straight up because I think it's the same thing?
No. No, you do. I mean, these could result from some other solution that would not then not that would choose different items that would then not lead to the optimal solution of 19. Yeah. So 19 and 17, there's a difference, right? That means that I must have chosen to take it, right? Because if I didn't, then they would be the same, right? 15 to 15, that just got copied down. Right? Now it could be that 15, well, it didn't get copied down. It actually got copied from somewhere over here, but then that leads to an equivalent solution. Right? You take these 3 items over here, you take these 3 items over here, it leads to the same value. That's perfectly fine too. There might be more than one optimal solution, but by using this table here, we're always looking up and saying, all right, well, did we take this item or not? The which one? 19 minus 17. That's the value of taking, what is it? Yeah, the difference between these two has no meaning, right? Because they're different, so I must have taken some value over here, right? 12 plus the value of A5 is 7. So 12 plus 7 gave me 19.
The 2 in that case would be like the difference between the best value you can get with A1 for A4 at weight 7 and the best value you can get A1 for A5 at weight 7.
Yeah, but that's the best interpretation you can come up with.
Only considered A1 through 4, 7 is the best.
Yeah, with the same weight capacity here.
Yeah.
The difference between these two, as he just said, is that, well, what's the best that you can do between choosing some subset of A1 to A4, and then this one is, well, what's the best one that you can choose from A1 to A5? Both of those scenarios with the same weight capacity here. Yeah, the pseudocode is super simple. The hard part is coming up with the recurrence, right? Again, this one is you have no choice. It's infeasible because taking the ith element means that you have a negative weight capacity now. If it is feasible, then you still have a choice. You can exclude it, or you can add it in, add that value in, and then you have some other value somewhere else in the table. Right? This is where that 19 comes in. Right? The 19 comes in as, here, let me go ahead and erase all of this. And let's look at the continue erasing here. So what is the value of 5, 7? Let's actually write this out, right? This will be the last thing that we do, and then we'll review this on Monday, right? So what is the value 5, 7, right? This is the optimal value of items A1 through A5, in other words, all of them, with capacity 7. Now, first of all, is it feasible, right? To take, you consider A5, right? Do you take it or not? Well, if I took it, then that means that capacity 7 minus the weight of 5 is that, what's the relationship with that and 0? So 7 minus W5 is 3. So that's equal to 4, and that's greater than or equal to 0. In other words, taking it is feasible. All right. Now, let me make this smaller and just move it over here. There we go. All right. All right, so now you have to consider two choices. Take A5 or leave it. So if I took it, then that means that my weight capacity is updated. V sub I minus 1, J minus W of I is equal to V sub 4, right, because I is 5, right, and J is 7 minus W sub I. That's equal to V sub 4 and what? 4? There we go. Which is going to be 4 and 4 right there. There's where the 12 comes in. All right? So this value is 12 plus the value of the item that I'm taking, which is 12 plus 7. That gives me 19. Right? Now, I still have to consider leave A sub 5. In which case, I've got V sub 4 and the same capacity here, which is equal to 4, 7. That's the one right above it, 17. Right? Now what you do is you compare this one, and then you take the max. Which one is it? It's this one. That's why it changes. Right? If you take it, then that means that you're changing the value. If you leave it, then you're doing no better than you were doing before. Right? That whatever value of what you had stolen so far, that stays the same, right? And that number would stay the same. Right? If you find an improvement, though, you automatically take it. All right. We'll go ahead and review this a little bit more, maybe even do some of this on Monday. And then we'll also, of course, talk about the pseudocode for regenerating that table, which is right here. Right? All you have to, and it's going to be a couple of while loops. Why? Because you're going to start here and you're going to travel up the table, right? You're going to jump over here, travel up the table, jump over here, travel up the table until you've fallen off the table's ends, in which case that's where the while loops come in. Right?
So you run that one on the table to get your solution.
Yep, this one generates the solution. It outputs the optimal knapsack S after you've got this completed tableau of V from the dynamic programming solution. You start out with an empty set. You start out at the bottom right of the table, right? And then you go through and go up the table and through the table until you've fallen off the table. That's what these bounds are for. Okay. Otherwise, next week, next week is the last week before the break. On the break, we will not have that Monday class already. That's already been planned for. But next week, we'll be done with dynamic programming on Monday. That leaves Wednesday and Friday, and then 2 weeks after to go over complexity, which is the last topic for the course. Right? As far as homework goes, you only have 9 and 10, right?
9 is part A and B, is that still 9? Right?
Say what?
9 has part A and B. So
Part A? Yeah, there's 2 programming parts to it, right? There's optimal binary search trees and this. In fact, that's all. I don't think that there's any written on it, is there? Yeah, it's something like that. So optimal binary search trees and the 0-1 knapsack problem. Those are that's 9, and then 10 is half written. There is a programming part on there, but it's worth 150 points. We graded out of 100, so you can get some bonus back with it. Right? Not for this class, no. I don't know. Well, I mean, Wednesday and Friday are the break, and then I've already canceled the Monday class, right? You want me to? we can do something.
I'm good.
Say what?
There still can be classes Monday and Tuesday, right?
There most certainly can be, yes. On Monday and I've always thought that they should eliminate fall break and then just move it officially to Thanksgiving break. The problem is then you have such a long period to the actual break, and then you've only got 2 weeks, and then you've got the full winter break. So that does kind of suck, but we did it during COVID, and it worked out fine. All right.